Hey everyone. So I guess just this is way over. And I wanted to just make one last video on acid and base titrations and buffers because I know this was personally a topic I found difficult when I took AP chemistry long ago. I think this semester has been sort of challenging because of everything being online, and this was definitely a challenge for me, even though it's my last semester I'm graduating, because I never took this class before, and just like how everything was new for you, I was also teaching myself along with all the lectures and reading through all the textbooks and everything. So I think that made this a little bit of a challenging experience. Yeah, so this will be the last video I guess I ever make. I'm just making this, I guess, just out of my goodwill, because GSS is long over last week. I don't have a lot of finals, I only have one. So I just felt like I wanted to do this. This will be my last video ever in undergrad, and that feels really weird. Okay, so I guess just to recap this, I'm gonna go back and use my GSS as a clutch. So you can see this screen now. Yeah, you can apply to be a GSS leader. I think it's due May 23rd, but that would be a wonderful experience. I know it's really challenging, and taking up being ready to take up that challenge is difficult, and it's a lot of nerve-wracking feelings, and it's just you can be really anxious, but I think it's a great opportunity, and you really get a good mastery of the material. Okay, so I guess here, what is a buffer? It's a mix of an acid and a base, and its conjugate base. And it resists the change in pH. So once again, weak acid is conjugate base, or weak base is conjugate acid. So you remember there are a bunch of examples here. This is how you solve or derive the Henderson-Hasselbalch equation. You can see here. So it's just simply an equilibrium equation, and all you did was do a negative log of both sides to get pH and pKa. And you have the A over HA, so you can see here. You can follow that yourself. There's two factors that really impacts it. The Ka value, which is like your equilibrium constant, everything has to do with that, and that's the overlying theme in the class. And the ratio of the two bases, the acid and the conjugate base. That shows like how much of the buffer, what percent of the buffer capacity you are in, how much you have used it. So the more concentrated these weak acid and conjugate bases species are, the more acid or base can be neutralized. So that means if you have a greater concentration, you have more of the buffer, you can neutralize more acid or base and resist the pH change. And the less the change in pH of buffer, this is a measure of buffer capacity, the ability of a buffer to resist the pH change. So I guess there are multiple types of problems related to this. I'm doing this video kind of blind, so I'm sorry if this ends up a little long. You can just speed up the video if need be. Once again, another reason why the acid and base are both weak is because when you remember looking at a table, let me see if I can pull up like a table. I think somebody was nice enough to have the table here. Let me see. I think it's somewhere here. I think it might be the spreadsheet, yeah. So if somebody was nice enough to create these, put these tables in this doc with the textbook values. Also, this one's not complete, so you can feel free to fill these in. They're conditional formatting, so if you type something in, it'll just turn white. It took me a long time. I typed these values from your textbook, but if, it'll be quick if you guys finish that up. here's the overall outline of all the topics. I think it's in GSS 19. It's on the very last slide. Right here, outline of all topics, and you can click that. But you can see right here in the textbook values. So there's always strong acids and strong bases. And you have the strong acids having the very big Ka values, and you have the strong bases having the very strong Kb values. And in the middle area, so like there's going to be Ka, like if it's really, really high, or Ka is very, very low, then that's strong bases, and this is a strong acid. Anywhere in the middle is sort of where you can get buffers, because they're kind of not strong bases and not strong acids. So this is where you get weak acids, weak bases, or kind of moderate, and that's where your buffers lie. Sorry, I stopped sharing screen. Okay, so I guess going back to this, I wanted to solve out a problem. So there is this problem, how to calculate the pH of a buffer. I don't think I ever solved this problem like completely out for you guys. Maybe I did, but I don't think I remember doing that. But I do have that. So first you want to calculate the pH of the buffer. So it says a buffer is prepared by dissolving 47.13 grams of NaNiC. So niacin is nicotinic acid, and it's not nicotine. It's actually niacin, which is like vitamin B3, and it's found in these foods like broccoli and all that. So you can see here. And it reduces cholesterol and reduces heart rate risk, and so, or heart attack risk. And then you have a buffer because you have, let me see if I can just, give me a sec. I'll just move this problem onto here. Okay, that's better. So you can see the problem right here. So the question, I already did this in 1GSS, is how you calculate a pH of a buffer. And that's going to be really crucial for titrations. So you can see here, it has NaNiC. Oops. Let me see if I can. Oh no, I hate how my slides are so colored. It's kind of hard for me to choose a color. So you can see right here, there's NaNiC, and this is a base. So because you can see it's Na plus and NiC minus. And you can see right here, there's sorry about that, HNiC, and this is the acid. So this is actually just NiC minus, and that's the conjugate base, and this one is the acid. And so you want to identify the acid and the base first. So it's asking for the pH of the buffer. It's saying you're dissolving this many grams of NiC in 1.25 liters of a solution of this concentration of acid. So yes, we're given a concentration right here. Sorry, this is really hard to see, this concentration, but here we're not. So initially we have to take a step back and we have to calculate that. So we're given, so if we are doing this, then we have 47.13 grams, and we need to convert it to moles to get moles per liter. So they're not giving the niacin molar mass, but you can Google it. So I guess we can just Google what niacin, NaNiC's molar mass is. So NaNiC molar mass. So I think you could just Google sodium So it gives you niacetonic acid, sodium nicotinate, and this looks right. So its molar mass is 145.09. Yeah, so this is the molar mass, 145.09. So if we go back to our whiteboard, so we do 145.091 grams. I got that from somewhere else, but so you do that for mole NaNiC, and you should get 0.3248 moles of NaNiC. And so once we get that, we just need to divide by volume to get the concentration, or what we want is NiC minus concentration. And so we can get, oh, remember there's 1 mole of Na to 1 mole of NiC minus, so they're equivalent. This is equivalent to this. So we just need to do 0.3248 moles divided by the volume, which we're given as 1.25 liters right here. And so when you do that calculation, you get 47.13 divided by 145.091. So then you can, so you get 0.0260 molar of NiC minus. Sorry, my handwriting might not be the best. Okay, so once you get that, all you need to do is use Henderson-Hasselbalch, because HH, so I'm going to abbreviate HH, Henderson-Hasselbalch. It's only used for buffers. It's used when you have a mixture. So remember, buffers are a mixture of a weak base and acid. And they are conjugate pairs. So I guess like for this one, once you get that, all you need to do is do pH equals pKa plus log of the conjugate. I always remember as a conjugate. So in the acid, this is a I guess in this situation, it's an acid situation. You also want to target and say this is an acid situation because we're given an acid and its conjugate base, which is NiC minus. I guess it doesn't really matter because you could do it the basic way, but I'm just gonna do it the acidic way because it's easier, because usually you measure things in pH, so usually the default is doing the acid, but it's valid to use the POH equals pKb plus log of the conjugate acid over the base. That's also valid. In this case, we have the conjugate base over the conjugate acid, over the acid, sorry, the acid in question. And you might be asking, why are we doing this? And the reason why is just simplicity, because they gave me both Ka, and they gave me Kb. And so I have both, but like personally, I think it's easier to use Ka just because they're asking for the pH, so I don't want to have to calculate the POH and then go calculate the pH. But either way, it's going to give you the same answer. So do whatever one's simpler. I guess for this one, you get pKa. So remember what pKa is. pKa is actually 10 to the Ka. I'm sorry. I totally wrote that wrong. Sorry, it's negative log of Ka. 10 to the pKa is, I believe 10 to the negative pKa is your Ka. But anyhow, so you do negative log of the Ka value, which we had earlier as 1.4 times 10 to the negative fifth plus log of what's the NIC. So right here, we see this Ka value right here is 1.4 times 10 to the negative fifth. You can see right there, it's 1.4 times 10 to the negative fifth. Okay, and then right here, so that's where that value comes from. So then we see this value right here is what we want to put for the NIC. So we will write 0.260 molar, all divided by 0.295 molar, which is the original concentration we were just given, which is right here, of the acid itself we care about. So once we calculate that, we get pH equals 4.80. So that's the answer to part A. So this is the pH of the buffer. Okay, so that's pretty simple. We just used Henderson-Hasselbalch. So if you want an order of this, you just use Henderson-Hasselbalch, basically. You just need to find the concentrations, find all the unknowns. So the pink guy, the blue guy, and the yellow guy, you just need to find all of those. For this one, we had to calculate the concentration and backtrack, but we found the pH. The next one's calculate the pH of the buffer after 1.1 molar HNO(C) is added. So all of these parts are a little bit more tricky. I'm going to go back to the slides. So I'm going to see if I can I'm going to pause the video for a sec. Okay, so then the next part is right here. So you can calculate the pH of the buffer after 0.1 mole of nitric acid is added. And so this part is harder because then you have to consider what's going to happen when you're adding strong acids and bases. And that can be more tricky. So the first one was the base case. I'll call it a base case. It's not because it's a base. I just mean it's like the original case. No strong acid, strong base, etc. added. So you're not testing the solution, it's just as it is a normal buffer. Initially with nothing added. So you're not testing it yet. It's like if you want to think about like exercise equipment, like you've just bought it and you initially tested this capacity, but you didn't really put it to its extremes yet. That's a really bad analogy, but okay, so here, calculate the pH after this. Okay, so you have to understand, recognize that this is actually a strong acid, it's nitric acid. So if you're going to memorize the strong acids, it's nitric, perchloric. There is hydrochloric, hydroiodic, hydrobromic, hydroiodic, and you have one more, which is sulfuric. So there's 6. And in this case, we're caring about nitric acid. So I just have these memorized from like high school. I don't know why I have that memorized. Okay, so you recognize a strong acid, and then you need to write is. So the question is really asking when you add bases or acids. Strong acids are a source of H+, and strong bases, so you have weird cases sometimes, like you have ammonia, which isn't a strong base, but it's a base, and doesn't have OH, so it's usually a source of OH minus, or removes H+. that's how you can think of what happens when you add a base. It will remove the H+. And so this is a source of, I'm just drawing a single-headed arrow because it's not at equilibrium, because its Ka is so high because it's a strong base. So you're assuming it's completely dissociated. Okay, so you have H plus and NO3 minus. So that's the dissociation. You're gonna, so I guess first identify ID, what is added? Strong acid, strong base, like what are you adding? 2, write the dissociation. Expression. Okay, so we wrote that out. And so it's a source of hydrogens, or protons. And so when we do this, we write that dissociation out, and we can see that we're adding 0.10 mole of HNO3. So if we're adding this is just stoichiometry, right? There's no equilibrium, only stoichiometry. There's no equilibrium because this is a strong acid. I'm sorry if I'm repetitive. There's 0.100 moles of HNO3. This is a 1-to-1 mole expression. That means you have that much H plus as well. They're all 1-to-1. So you can see that you actually have 0.1 mole of H plus. So that's how much is added. And so we can just divide this by the volume to get the concentration. So this is just number of moles, it's not actual concentration. So you just need to divide 1.25 liter, which was the total volume we said earlier. Just assume that volumes are not additive in this example, because they don't say it is. But if it is, then you have to consider that, because it will dilute your sample as you keep adding more. So this is 0.08 more of protons added, and then you go back to your other system, which is the buffer. So we're adding to HNIC. So this is also related to sort of like the Chatelier's principle. So sorry, it's at equilibrium, so it's H plus NIC minus. So this is the nicotinic acid. You do ICE table for it. So you start with 0.295 molar. And you have 0.26 molar here. The reason for this is because you'll add 0.08 more to your HNIC, because when you add protons to the system, you shift left, and so you'd be adding. So remember Le Chatelier's principle. This is, I know, confusing, because if you think that you're adding H, you'd think it's adding to here, but because this is at so then I guess number 3 was the stoichiometry to find. I'm sorry, I'm going back and forth to find H plus. Okay, so then that goes to number 4, equilibrium. And for equilibrium, remember Le Chatelier's principle. So you need to write the expression and consider Le Chatelier's principle. Because it's going to shift the equilibrium left or right. So we're carrying at equilibrium. We don't care about the initial values. We're carrying after some time has passed and it equilibrated, what are the concentrations then? Because, we care about what the buffer did, not what's going on initially. And so the 0.295 here is what we got earlier from right here. That's how much we started with for concentration of HNIC. The 0.260 is coming from the amount of NIC we had initially, which is 0.26 we calculated earlier, right? So because it's in a one-to-one relation with H+, if you have 0.26 more of NIC, that means you have 0.26 more of protons, because they're in a one-to-one stoichiometric relationship. So these are in stoichiometric relationship, but these are not. The reason why is it's at equilibrium. Remember, your Ka value is going to shift it left, or it's going to shift it right. And for this case, it's going to favor, it's a weak acid, so it's going to actually favor more of the acid form, undissociated acid. So this is undissociated, and this is dissociated. So it's going to favor more of the undissociated acid. I'm so sorry. I think I might have been talking without sharing the current screen. So I guess once again, we just need to ID what is added. Is it strong acid or base? And so we added nitric acid. And strong acids were a source of protons. Strong bases are a source of hydroxide, or removes protons. And so you just have to write the dissociation expression. You do stoichiometry to find the protons. And it's only a stoichiometry problem here, and there's no equilibrium because this is strong acid and completely dissociates. So 0.1 mole corresponds to protons, and you divide by 1.25 liters to get 0.08 more. That's the number of protons we have being added. So that goes to change because it's the perturbation to the system. And so that came from here, what's added. Perturbation. Remember, for the Le Chatelier's principle, it's always a perturbation to the system. So for your equilibrium part, you want the expression. For the buffer, you want Le Chatelier's principle. So just the dissociation expression and Le Chatelier's principle. And so right here, once again, we see that Ka is small. I'm so glad I checked that. I wasn't sharing the right screen. Sorry about that. So Ka is so small, and so it's going to favor the undissociated form rather than dissociated form. And so that's why you see a concentration of HNIC is actually higher than these two. But remember, these two are in stoichiometry. So they are one-to-one. And so because these are one-to-one, we know that the 0.26 right here is one-to-one with the 8 protons. So we know what the initial protons are. This was from the initial concentration. It was 0.295 molar of HNIC. And so all we need to do, sorry, this is so slow, but you just need to add 0.8 more, subtract 0.8 more from the right side. So the reason why we're subtracting here and we're adding here is because Le Chatelier's principle, what are we adding? If we're adding more H plus, right? So this is going up, then we're adding a pressure onto the right side. To alleviate this pressure, it's not real pressure, we need to go left. Shift. We need to shift it left. And so because we're shifting it left, we add more concentration to HNIC. We subtract from the right side. And so once we get, what we get is 0.375. I hope this is helping you really conceptualize and understand how this works. 0.18, 0.18 more. And so once we do this, all we need to do is Le Chatelier's principle again. I'm sorry, not Le Chatelier, Henderson-Hasselbalch, because this is for a buffer, and we were asked to calculate the pH after of the buffer after this much was added. So all we need to do is pH equals negative log of the Ka value we had earlier, that doesn't change, plus log of, just need to do log of 0.18 molar divided by 0.375 molar, and we get the pH. So we're just dividing this guy by this guy. Because we do base, conjugate base over acid, and we get pH of 4.53. Okay, and so once we do that, we're going to consider the third question. Also, we can double check this is right, because here it's 4.8. If we're adding a strong acid to the buffer, we're going to assume the pK is going to go down. And the pK does go down. It goes to 4.53. But I guess the change wasn't too big because it's not like 1 or 2. And you can calculate the pH of HNO3. Like, you could calculate the pH of this guy. And if you calculate the pH of that, that's negative log of the number of protons you have, which is 0.08. That's like a pH of 1. So this strong acid, nitric acid, had a pH of like 1.010 or something. That's very strong. But then you'll notice that the buffer is doing a pretty good job because it's not close to 1, it's closer to 4.8, which is the pH of the buffer. So check for the sanity check. Lower than pH of buffer, which is 4.8, but closer to this value than the added nitric acid. Okay, so then once you do that, you can look at the pH of this guy. And so I'll just go through this quicker because I think now you have a better understanding. So we just are adding a strong base this time. So number one, ID. So to ID this, we say it's a strong base. And so we have OH, so it's a source of OH. We can treat it like a POH problem maybe. And so we're given 5.0 grams. That's kind of annoying. So 5.0 grams of NaOH. All you need to do is find what the molar mass of NaOH is. You can add like whatever it is, 22 plus like 16 plus 1. You get 0.997 grams of NaOH, 1 mole of NaOH. So that's, again, 1 mole of NaOH is 1 mole of OH minus. And so you could get, and remember OH and H plus are 1 to 1. So it kind of doesn't matter if you approach this. So it doesn't matter if you approach as losing protons. Like, so if you ever have like ammonia, you're going to have to do losing a protons like method, or you could do OH added. And that's, you could use like POH and the pH to POH relationship, and that'll make it easier. And so once you do this, you find this is 0.125 mole of OH minus. Okay, so this is a strong base. It reacts with, so H plus OH minus gives you water. So it's 1 mole to 1 mole. That's the stoichiometry of the H plus to OH minus. And so once you do this, all you need to do is find that what's the concentration of OH minus. So that's equal to 0.125 moles over 1.25 mole, sorry, 1.25 liters, and you get 0.100 molar of OH minus. And so what we need to do is it's going to actually shift it the other way. So when we do you can do this whole table again, but basically the main point is, again, Le Chatelier's principle. Okay, so I'm just gonna copy and paste I'm just gonna copy and paste this guy once again. Oops. Okay, so I think that looks great. So what we're just doing is technically another ice table idea. So we're adding, when we are adding OH minus, it's the same thing as removing H plus because they react. And so the question here is, if we remove H, what happens? We need to drive the system right. And so we'd add to the right side. So we add 0.100 molar plus 0.01, I'm sorry, 100 molar minus 0.100 molar. So if you do another ice table, this is the same thing as before. Both of them are the same, 0.260, because so each of the parts are not related to each other for this problem. They're just asking you in different scenarios. And so what we just get here is 0.195 molar. We get 0.360 molar for both of these because they're, once again, 1-to-1 stoichiometry. So you're just going to use Henderson-Hasselbalch, once again, rinse and repeat, negative log of 1.4 times 10 to the negative fifth plus log, I'm sorry if my handwriting is so far, of 0.360 molar over 0.195 molar. And so you get the pH to be 5.12. And so that's expected once again because it's slightly above 4.8. So if we do a sanity check, so we notice it's slightly above because we added a base. And so if you actually calculated what this 0.1, you could find pOH by just doing negative log of 0.100 molar. And you could do just 14 minus the number, I think. 0.1. Yeah, so if you do 14 minus, so the log of 0.1 is actually 1. So if you do 14 minus 1, pH equals 13. That's pretty basic. The pH of the NaOH was 13. So we can see the buffer is once again doing a pretty good job the other way because it's closer to 4.8 than 13. Okay, the last two, this one's harder. You have to assume there's a volume that's additive. So this time, this problem added a mass, right? So this is an example of a mass. Oops. See if I can. So this one was an example where you added a mass of something. This one was an example where you added a mole, the moles of something. They're gonna give you an example of where you're adding volumes of something. So right here, we're adding volumes. The last one is the hardest, but okay, so once we do this, it says 95 milliliters of 5.0 molar concentration of HCl. Again, ID. So we ID as a strong acid. HCl is a strong acid. And so all we need to do is, we realize it's 5.0 more of HCl. So we just need to do 0.095 liters, but the volumes are additive in this example. So that means we have to just calculate moles. Okay, so when volumes are additive, volumes are not constant, concentration is not constant. But moles are constant. Same thing as mass, but moles are constant. And so because moles are constant, moles really run this problem. And so you just have 5.00 moles of H plus over 1 liter of HCl. You know, H plus and HCl are 1-to-1, so I'm just going to skip that step. And so you actually get 5 times 0.095, that's actually 0.0475 moles of H plus. And so once we get that amount added, we usually would take the moles and divide it by the volume, right? But in this case, we had 1.25 liters V initial plus V added. So we add 0.095 liters, and so we can get a value of 0.0627. I'm sorry, I don't know why I wrote that. 1.25 plus 0.095 is 1.345 liters V total. So we're doing a volume balance essentially here. And so once we do this, we can just take this number and divide it by the final volume, which is going to be 5 moles of H plus divided by 1.345 liters equals what your H plus value will be. 0.475 divided by that. So you get about like 0.353. The one thing about this though is, so this part, you can do it this way, but another shortcut that's actually simpler and you could just plug these into ice, but another simpler way is just use moles. And so all we need to do is do ice table, but only with moles this time. So if I copy and paste this guy back in, sorry, it's kind of weird. Okay, so here we have we have 0.295 molar once again. But we know that we want to convert the 0.295 molar and the 0.260 molar. We need to convert those to, so this was for H Nic, and this one was H plus and Nic minus. So we need to convert those to moles from concentration. And so what we do is we just need to multiply 1.25 liters, which was the initial volume. And so when we do that, we will get times 1.25. So you get 0.369, and you get 0.325. And so we just need to use 0.369, 0.325. Again, we're using Le Chatelier's principle and said earlier, like the acid case, we're adding more H+. So this guy goes up, so you just need to shift left. And so you're going to subtract out 0.475. And you're adding 0.475 molar here. But we noticed something weird. The question now is, oh shoot, we are getting a negative number. Okay, so then this becomes a problem. And so what this means is, in context, it means buffer capacity reached. And so basically what we did is we used up all the buffer. Used up. And so this is similar to where it would tie into like titrations. And so because you got something negative here, all we need to do is we just need to figure out how much was left over. And so we can figure out how much leftover we had. So that is actually, so we do 0.325 minus 0.475, and we'll get like 0.15 moles, sorry. And you divide that by 1.345 liters, which is the total. And so if you divide that by 1.345, you should get like 0.112 molar. And so that's the amount concentration extra. And so we just need to now simply do, so if we didn't have used up all the buffer, this means all we have is just a solution of HCl. So I guess I don't want to type because it's going to be loud, but if we used up all the buffer, all we have now is the strong acid or strong base, but the strong acid. So we treat this as a strong acid problem. This ties into titrations because titrations will test out the whole buffer capacity over range, which we'll talk about. That's the next thing I want to talk about. I'm sorry the video is getting long. Please feel free to time speed it. So what is the formula for pH of a strong acid? If it was a weak acid or weak base, you just treat it as a weak acid or weak base problem. So that means it's just an equilibrium problem. So if it's a strong acid or strong base, you just do the pH equals negative log of H plus, or POH equals the negative log of OH plus, or I'm sorry, OH minus, I'm so sorry about that. And pH plus POH equals 14. So you can use those relationships. Here, this is log of H plus, which is 0.112 molar. And so we get the pH to be equal to 0.952. And so if we do a sanity check on this, I'm sorry, I'm like freezing up. Okay, so if we're doing comparing this guy, and this guy, we can see here it's much, much lower. So we went way beyond the pH buffering capacity. And so the pH is actually closer to whatever value. So if you see it was 0.353 molar, if we did a negative log of this, 0.353, we can find that the original acid, this 5.0 molar HCl, originally had a pH of 0.45. And how did I find that? All I did was do the pH negative log of 0.353 molar, which was the H plus that I had initially that we calculated. And so it was like 0.452. And so when we compare these two, we can see it's still higher than 0.452 because the buffer did do some of its job. But because we went beyond, it's much, much lower. It's closer to the acid added. It's not close to 4.8. So the pH is closer to that of the acid added than the buffer. Okay, so the last part, how many grams of NaOH must be added so the resulting pH is 5.0 for 5.5? Use algebra. So this part is actually probably the trickiest problem. I don't know if Dr. Dodson would ever ask something like this. Hopefully not, because I know this one was stumping me for a long time. So it's asking, it's like a backwards problem. It's asking for the pH, I'm sorry, it's asking for the mass of NaOH, which is a strong base. So its resulting pH is 5.0 or 5.5. And so it says hint, use algebra. Yeah, so this one is not a fun one. So we do pH equals pKa plus log of Nic minus, which is the conjugate base, over HNic. So what we need to do now is we have the pH, we have the Ka, we want to find the ratio of HNic to Nic. So find ratio of Nic to HNic. So we have this and this. Okay, so what we can do is we can rearrange. So if I do Nic minus over HNic, so remember if I just subtract pKa from this side, so it's pH minus pKa, and if I just do 10 to the this 10 to, so if I just do this, sorry, I'm gonna use a different color. So minus, I don't know why it's like this. Okay, so minus pKa, minus pKa, and then you just do 10 to the, and then you'll do 10 to the. So you're gonna get 10 to the pH minus pKa. And so what we do is we'll find that that equals 5.50, that's the resulting pH we have, minus the pKa, which is actually the negative log, so we'll just add plus log of 1.4 times 10 to the negative fifth, which is the Ka value. Then we can get this to be equal to HNic. And so when we do this, we also need to consider that Nic and HNic. So these are the final values, right? At equilibrium. The question is asking how much must be added. So we're looking for the mass change. So the C part, we're looking for the C part. They're giving us the equilibrium part. And so we remember that from the ice table, Nic minus at equilibrium equals the Nic minus initially. So I'm going to put a knot here. It's initially plus X. So we need to use Le Chatelier's principle once again. So we're adding X because, look, we're adding NaOH. So when we add NaOH, we're increasing the H plus. So we're going to shift right. And if you don't understand why, go look back at the base example. We're shifting right because we're losing protons. So we add X to a Nic, and HNic is on the left side, so you're going to subtract. So it's going to be HNic initially minus X. And so we can replace these expressions right here into right here. And so when we do that, you're going to get this whole crazy algebra, which I don't like, but Nic minus naught plus X equals 10 to the pH minus pKa. So this whole value is actually, I didn't calculate it out, but let me do that. So when you do 10 to the 5.5 plus log of 1.4 e negative 5, you get 4.427 or 43. So I'll just call this 4.43. And then you get HNic naught minus X. And so we just need to solve this algebra. Nic minus initial plus X equals 4.43 times HNic naught minus 4.43 X. And so when you combine these, you get 5.43 X, 4.43 HNic naught equals that. So, and we were given these originally. So remember the Nic minus was 0.260 molar minus 4.43 times 2.295 molar equals negative 5.43 X, or all divided by 5.43 would equal X. So X equals, so let's see if we can do this, times 0.295, 26 minus that, divided by 5.43, sorry, there should be a negative right here too. Then you get 0.193 molar added. And so we finally found a change. So X is the change, but this is not finished because we know that's a concentration of added OH minus. So what we need to do now is do 0.193 molar OH minus. We just do stoichiometry to find slash unit conversions to find mass. So we just need to multiply by 1.25 liters. because this is moles per liter. And then once you get number of moles, gotta convert that, so use the molar mass. I'm sorry, I'm getting a little tired. 997 grams of NaOH. And so when we do this, we get 9.64 grams. So you probably should be able to do this backwards as well, but I know this was a tricky problem. And so that's how you get the answers. I hope that helped, and this is the solution to that GSS problem in GSS 17 and 18. We never solved it out explicitly. And so, yeah, I hope that helps. And we're gonna go back to titrations. So I'm gonna go back to the slides. These slides, sorry. Okay, so for titrations, just to run through once again, you have a procedure for solving these problems. Like earlier, I said there was stoichiometry problems and equilibrium. The stoichiometry is mainly for when you have strong bases and strong acids. So for titration of weak acid with strong base, the reaction of OH minus with a weak acid is assumed to run to completion and the concentration of the acids remaining and the conjugate base forms are determined. Same thing here. It's just a reverse. For titration of weak base with a strong acid, the H plus with the weak base, so the reaction is OH minus with weak acid in this case, the H plus, so you're adding H plus because it's a strong acid. Here you're adding OH minus because it's a strong base. You're starting out with a weak base, so you're starting out with a high pK, or pH, sorry, and the weak base is assumed to run to completion. Same thing here, but equilibrium. So you're going to use a weak acid equilibrium to govern because the buffer was a weak acid and you're titrating with a strong base. For the weak base problem, it's a weak base equilibrium. So here you're using Le Chatelier's principle. So H plus will react with the OH minus, as we said earlier in the buffers part. You have ice tables in the 5% rule. I guess the 5% rule doesn't always apply, so please check that. Usually it should because they're weak acids and bases. Buffers and Henderson-Hasselbalch expressions. So there's 4 parts of a pH titration curve. So first part, you calculate the initial pH of the weak acid or base solution by treating it as a simple acid or weak acid or base solution. So here it's a weak acid. We're going to just assume it's a weak acid problem. There's no, right here, there is no conjugate base. The buffer has not been used yet, or there has no, I'm sorry, there's not even a buffer in the solution because there's no mixture. This is the buffer region. You have a mixture. Right here, you have only weak acid. So you treat it as a weak acid problem, equilibrium problem. And then as you add a strong base, so by Le Chatelier's principle, you're adding OH to the solution. So this weak acid will dissociate and create some of its strong, or some of its conjugate base. So the idea here is, so you have a weak acid. As you add OH minus, for instance, you'll have your weak acid, and you'll create your conjugate base plus your H plus. And so as you're adding OH minus, you're using up H plus, and so, you know, your equilibrium shifts right. And so as you shift right, the conjugate base is formed. Yeah, so that's the idea. So you're creating a mixture or buffer by adding OH minus. So then furthermore, so the question is, what is that? That is a buffer solution. And then now all you're going to do is determine the moles of acid consumed. That will be the moles of conjugate base formed. And so remember, the stoichiometry part of this is that these are 1 to 1. The conjugate base, so anything on one side of the equilibrium expression is in there's a stoichiometry to it. I'm sorry, my voice is going out. So anything on one side is in stoichiometry with stuff on that side, not on the other side. Because on the other side, that is determined by Ka and Kb values. Okay, so once you have that, then calculate the molar concentration of the weak acid and conjugate base, taking into account of the volume of titrant added. So as you add the volume, this additive volume, you're gonna treat everything by using the moles, just the number of moles, as we showed in earlier. And then finally, we can do a Henderson-Hasselbalch, because you're gonna find, so the HH expression was pH equals pKa plus log of Cb over A. And so what we will need, the four things we need, well, we have pKa, that's from a table in the appendix. So you should have that at hand if they don't give it to you. The pH, so there's actually really three variables here. The pH, the conjugate base concentration, and the acid concentration. And there's also the invisible variable of H+, which sort of is like related to that, but it's also related to your conjugate base, because H+ is 1-to-1 mole ratio with a conjugate base usually, or the conjugate, just conjugate base. Okay, so I hope that helped. And so the third part, you're going to use that expression, and you can see here, it's the same thing here. You treat it as a weak base solution for the weak base titrated with strong acid, and as you add acid, you're shifting the equilibrium left, and because you shift the equilibrium left, you're getting more of the undissociated acid. And so as you get more of the undissociated acid, you're in the buffering zone, and then you hit the equivalence point and then go down. We're going to continue here. So the third part is the equivalence point. You treat it as the salt of the weak acid. So at the equivalence point, all the weak acid has been converted to its conjugate base or acid. So what this means is that your buffer capacity has been reached. So your buffer capacity, so this is your buffer capacity, right between here and here is the buffer capacity region. You can see by the almost straight line here, the pH is nearly constant. Once you reach it, it's going to immediately shoot up or shoot down. The reason why is now, okay, here's the idea. You have a weak acid at the equivalence point, all of it has turned into its weak conjugate base, or vice versa. And so you no longer have a mixture, which means you no longer have a buffer. And so that's why you cannot use Henderson-Hasselbalch anymore. And what you just need to do is now simply a conjugate base or a weak base problem. And so you'll treat it as a weak base solution. So it's the same as here. You're treating it as a weak acid on one side, you treat it as a weak base on the other side. If it was a weak base titrated with strong acid, same thing. Weak base problem, then, a weak acid problem. The only difference is you added volume, so you have to consider that. But the moles are constant and the volume is changing, so that's not too bad once you get the hang of it. So at the equivalence point, you have primarily the excess strong acid or strong base that will determine the pH. So afterwards, you used up all the buffer. So here you depleted all buffer. And so you're simply treating it as a strong acid or base problem. So that is a very simple problem, as we mentioned before. Negative log of H+ or negative log of OH minus. So that's very simple. Okay, sorry. So you can see that. I'm at clear screen. How do we treat strong acid and base titrations? What modification do we make to this procedure? Once again, we just use these expressions and pH equals 14 minus POH, and you don't use Ka or Kb because there is no equilibrium at this point. There's only equilibrium for 1 to 3, 4 doesn't have equilibrium. So this is not equilibrium. But these, yes, are equilibrium. So no Ka or Kb's. Hope that helps, and you can see the exact same thing here. And we already calculated this whole problem with the niacin. There was a morphine problem. We didn't go over this, but I think that there are answers right here that I gave you guys, so you can try this. So once again, the first one is you're just writing a balanced net ionic equation for the reaction that takes place during the titration. What are the species present at the equivalence point? At the equivalence point, you only get the conjugate acid. In this case, this is a weak base and you're titrating with strong acid. So you only have all the weak bases depleted at the equivalence point. So you're just going to get the strong acid and you will get the conjugate acid of this. So you get H morphine, whatever that looks like. So, yep. And then to work this problem out, you're going to treat part C as what is the volume of HCl required to reach the equivalence point. You're just going to do MB equals M1V1 equals M2V2. It's the stoichiometry problem. Because you know the number of moles at the equivalence point, the number of moles of morphine must equal the number of moles of H morphine. That means the morphine number of moles is the exact same as the H plus. And so the H plus can be equated. There was no H plus originally, so the H plus can be from hydrochloric acid. And so that's how you can do the M1V1, M2V2 stoichiometric relationship to get the volume. Part D and part D is just a simple weak base problem. Part E, so you're going to use equilibrium and ice table. Part E, what is the pH of a solution halfway to the equivalence point? So this halfway means you have the exact same concentration of morphine as its conjugate acid, whatever the acid is to this, sorry, H morphine, I'm just going to put H morphine. And so because of that, when you do Henderson-Hasselbalch, because the conjugate acid and conjugate base and the conjugate acid cancel out to 1, the negative log of 1 is 0. So you just get pH equals pKa. And then for the last part, you just need to it's similar to part D, you just need to apply a weak acid problem, and you're going to get this value. So I guess it says you can show the values if you would like. All of this. Okay, so right here, we did M1, sorry, I'm going to speed through this because I think it's getting way too long. M1V1 or C1V1, whatever concentration you want to call it, C2V2, and you can get 71.8. So it's 0.150 molar of morphine. It's titrated, and there's 50 milliliters of it. And it's titrated with 0.14045 molar hydrochloric, and we just need to find how much hydrochloric. That was simple. For this one, we treat it as a weak base problem. So you can do an ice table and use a 5% rule, and you can find the pOH, and from the pOH you can do pH equals 14 minus that to get 10.52. halfway to the equivalence points, pH equals pKa, or POH equals pKb. They give you a pKb or kb here. Once you find pOH, it's again simple. 14 minus pOH is 7.87. And then the last part, all we need to do is, so I just called it H plus morphine. This is very messy, sorry. You do an ice table again, but you're gonna treat it as a weak acid problem. And because it's a weak acid problem, the biggest relationship to remember is your Kw over Kb. So Ka times Kb equals Kw. So you can find Ka this way, and then from your Ka, you can use the pKa relationship, Henderson-Hasselbalch, find pH. And the volume is additive, so you gotta do this whole complicated thing. That's the only difference from part C. I'm sorry, my throat is like really hurting now. I hope this video was very helpful. I was gonna do another problem, but I think that might take a little bit too long. Also, be sure to review. You can look at all of these GSS. The last thing I have as your tips for your finals, identify what you're solving for, circle your unknowns, highlight them, find an equation that relates them, use unit conversions. I think I detail all of this in the whiteboard that I showed you earlier. Don't freak out. Panic is the number one problem. For all of these problems, I know I got stumped sometimes. You can take a break, come back. I mean, not on exam, but even like on exam, maybe take a minute break, come back, and then try to approach it a different way. Be level-minded and patient, and analyze it. Make it multi-part, split it into subsystems, solve, and integrate problems parts together. So I know on GSS 16, there were some salt problems. Oops, sorry. So it says identify the salts as basic or acidic. To do this, all you need to do is find where its sources. So this is Cl minus, so it's HCl, that's a strong acid. NH4's conjugate base is NH3. And so that's a weak base, and you know this is acidic. Whichever one dominates, whichever one is strong, is it acid or base, that dominates. If they're both strong, then it's neutral. And if they're both weak, you need to look at the Ka values, and whichever Ka and Kb values, which one is bigger, like Ka or the Kb, that dominates. That's how you tackle these. You can read over all of this, but the answers are here. Yeah, so I think that kind of summarizes all of this. Okay, so I think that's it. Like, feel free to look at all of these. I think I have a lot of problems on here. A lot of them are, everything is hyperlinked on here. Like, I gave you all the resources for GSS on this link. So I hope you make full use of it. I will try to put this in the Slack as well. So that's that. The electrochemistry part, hopefully you can also approach that level-minded, and there's a textbook values here. And once again, there is a quizzes here. It has 82 questions on it. So I hope this is really helpful. You can see here, you can click preview. When you click preview, you can click start, which will just allow you to, play. Yeah, it has music if you want music. It has read aloud, so it can read it out loud for you for some of these. And you can play this by yourself. So if you want to try this out, and it has, like, I think a timer. I guess the timer doesn't work when you do this by yourself. Go like, okay, how do I do this? Select all that applied, so I got it wrong. You can play this by yourself. You can also click show answers here. You can click challenge friends. I don't know how that works, but if you want to study together, you can do that. Flashcards. The flashcards is really neat because you can just flip the cards. It kind of treats it as a game, so I think you will enjoy it. So you can click flip, and then it'll tell you the answer, so you can try this out yourself. For instance, this one was like Henry's law, because it's like osmotic pressure. Sorry, it's not Henry's law, it's just osmotic. It's related to that unit, I don't remember. But I hope you guys all do very fantastic on your final exam. Justice is completely over, but I think this was a great last video. Here's the whiteboard. I don't know how to share this. Unfortunately, I don't think I can, but I'll try to put SVG file so it's high resolution. You can zoom in if you would like that. So I guess some of you wanted extra problems. I didn't do these extra problems out. There's a morphine problem. But if you would like, I just have a textbook in front of me right now. If you would like a few extra, I can just write some here and its answers as well. So here's a problem for a strong acid, strong base problem. I think they're simpler than a weak acid, strong base, or weak base, strong acid problems. So here it's 0.3175 molar solution of potassium hydroxide was used to titrate 35 liters of 0.257 molar hydrobromic acid, and you assume that the volumes are additive. And so for this problem, it says write a net ionic equation for the reaction that takes place during the titration. And so for this part, we just get, so anytime you have a strong acid and strong base problem, so actually not. So you'll just get H plus OH minus H2O. They form H2O. So that's your expression. And then for part B, what are the species present? So you're starting with potassium hydroxide. You're starting with hydrobromic acid. And you end up with potassium hydroxide. And so you're just going to be at the equivalence point, you get whatever you end up with, which is K plus OH minus. But then the OH minus is actually used up to make the hydrobromic acid dissociate. And so you just get Br minus. So you get K plus and Br minus. So what volume is added? I'm just going to give you guys the answers so you can check this later. 65.4 milliliters. You get for part D, or part C is what volume of potassium hydroxide is required to reach the equivalence point, 65.4 milliliters. What is the pH of the solution before any KOH is added? So you can just do a strong acid problem for part D, and you should get 0.590 as your pH. And for part E, what is the pH of the solution halfway to the equivalence point? You should get your pH equals 1.777. And for the last one, what is the pH at the equivalence point? You would get 7.00. But that makes sense because this is a neutral solution. Strong acid, strong base. Okay, so I'm going to I'll pause the recording once again and add another problem. So here's another problem. So this one's actually a weak acid, weak base, weak acid, that type of problem. So at 25 degrees Celsius and 1 atmosphere pressure, 1 liter of ammonia is bubbled into 725 milliliters of water. Assume that all the ammonia dissolves and the volume of the solution is the volume of the water. A 50 milliliter portion of the prepared solution is titrated with 0.2193 molar nitric acid. calculate the pH of the solution, A, before titration, B, halfway to the equivalence point, and C, at the equivalence point. So you can pause the video here if you want to try this out. Sorry, my handwriting is awful. I'm writing on the screen, like that's vertical. So the solution to this problem is for question A, the pH equals 11.00. Question B, the pH equals 9.25. For question C, the pH equals 5.30. And so this problem kind of requires you to think about solutions as well. So it's more integrative, I think, because you have 1 liter of ammonia, it's a gas, and it's bubbled into this amount of water. And you dissolved all the ammonia in the water. And so you have to use like PV equals nRT, and that way you can find the moles of ammonia you actually put in the water, and that's how you get concentration. So I'm going to give you a hint. So you have a strong acid, which is nitric acid right here, and you have a weak base, and so you get a buffer. So you start with a strong acid, start with weak base, meaning your pH is high, and then you curve down. So the titration curve would look something like this. This is just NH3, and then somewhere here you end up with only HNO3 pH. So I hope that helps you, and you can try out this problem. And right here is a little cool twist because you're going to have to think about gas laws. And so this is a pretty integrated problem. So there's this problem, and I think that's all I have really. I don't have that many other problems I can provide. For titrations, some other problems are after how much volume has been added. So that would be similar to like the buffers problem that we did earlier, except for the buffers problem we kept repeating from that base case. For that one, it's like a series, not a parallel. So I can give one more of those if that's helpful. Okay, here are the last problems. A 25 milliliter sample of a 0.100 molar lactic acid HC3H5O3, pKa of 3.86, is titrated with 0.100 molar of NaOH solution. Calculate the pH after the addition of 0 milliliters, 4 milliliters, 8 milliliters, 12.5 milliliters, 20.0 milliliters, 24.0 milliliters, 24.5 milliliters, 24.9 milliliters, 25.0 milliliters, 25.1 milliliters, 26.0 milliliters, 28.0 milliliters, and 30.0 milliliters of the NaOH. Plot the results of your calculation as pH versus milliliters of NaOH added. So you can pause the video here if you would like to try this problem out. Okay, here are the answers for this. So you're going to have the volume in milliliters. So I'll just write the answer like this, and your pH that you get. So at 0.0, you will get 2.43. At 4.0, you should get 3.14. At 8.0, you should get 3.53. At 12.5, you should get 3.86. At 20, you're going to get 4.46. At 24, you get 5.24. At 24.5, you will get 5.6. 24.9, you get 6.3. And then at 25.0, you will get 8.28. At 25.1, you get 10.3. At 26, you will get 11.29. At 28, you get 11.75. And at 30, you should get 11.96. So those are the solutions right there. And you can plot that on a graph if you would like. I don't think she will ask you to plot anything, so I wouldn't. This is like, I wouldn't worry about that too much, but you should notice that the volume, like the pH starts low and goes to high, so it'll probably look like something like that, where your equivalence point appears to be around like 5 or so maybe it's around like 5. And here it's around like 12, and here it's around 2.4. 2.4 is interesting. It's actually a pK of a carboxylic acid carboxy group on amino acid in proteins, and you'll learn about it next year. So deep respect to that. The last problem I'll show you is a sample of a certain monoprotic weak acid was dissolved in water and titrated with 0.125 molar of NaOH, sodium hydroxide, requiring 16 milliliters to reach the equivalence point. During the titration, the pH after adding 2.00 milliliters of sodium hydroxide was 6.912. Calculate the Ka for the weak acid. So this is a typical problem as you have an unknown and you're in the lab and found this like really old acid and we just don't know what the pKa is. So the answer, you can pause the video if you want. Answer is 1.74 times 10 to the -8th, and that's the Ka for the unknown. So I didn't try out all these problems myself, but I think these are pretty good problems. And so you can feel free to pause the video right there. Feel free to pause the video here if you would like to screenshot that. And then right here, maybe it's a little too small, but I will just show these slides. So right here, feel free to screenshot that if you would like, or pause the video. Here's this part. There's this part. Okay, and then there is lastly this part. And this part. Oops, I forgot about that. Okay, that result, I guess like ends and concludes the video. So good luck to all of you guys. Sorry it went very, very long. Feel free to 2x speed it. And yeah, I guess I'll graduate, but good luck with biochem in the fall and everything resuming to hopefully in person because, you know, online kind of sucks. Yeah, good luck, guys. Bye.